In the last unit, we saw how waveforms display frequency, so that's the frequency of the waves over time, and amplitude, the size of the waves in a sense. And we measured frequency in a complex periodic waveform of a sung vowel. We're now going to talk about how a complex waveform is made up of combinations of sine waves, how the spectrogram displays the amplitude of parts of the complex sound, and then we're finally going to get to the formant structure of vowels. So when we combine two sine waves, we can create a complex wave. So we're going to take a sine wave at 440 hertz. Now you can see this is at 440 hertz because this window is 110th of a second. So there'd be 110 of these in 1 second, and there are 1, 2, 3, 4 periods, so there would be 440 of these periods in a second. 440 hertz is actually an A in music. This one, you can see there's 1, 2, 3, 4, 5, 6, so this is 660. We combine those and we get this waveform. What's its pitch? Well, there's 1, 2 of these complex waveforms going through. So this is actually at the fundamental frequency is 220. And you can tell that it sort of sounds lower. Those two that we combine together, we get a sensation of a lower pitch sound. What's the frequency of this complex waveform? Well, it's 1, 2, 3, 4 again. So it's the same, it's got the same fundamental frequency, and we'll talk more about fundamental frequency in a minute, as the first one we got. What do you think the frequency of the sine wave was that we added to it to get this? So notice how the addition here, we had our 440 and our 660, and you can sort of see the remnants of the two of them in the waveform. When this is the average of them. Where did we get this one from? Well, look at where the peaks are. These are the peaks that were originally from the 440 plus something else, and this was the something else averaging with the 440. It's 880. This is 440 and 880, and you wind up with a pitch that's the same, because that's the 440 and 880. That's an octave again. So many instruments and the vocal folds vibrate at a fundamental frequency and at harmonics that are integer multiples of that frequency. So the fundamental and 5 harmonics are illustrated in this in string vibrations. In this graphic here, where we have a string vibrating at 1 frequency. Here it's vibrating at 2, at 3, at 4, at 5. So 440 and 660 are the second and third harmonics for 220 hertz fundamental. That's what we saw in the first display of combining the waveforms. And 880 would be the first harmonic for a 440 fundamental frequency. If you want to see a little bit more of strings vibrating at different frequencies, this YouTube video here linked is a really great illustration. So given a complex waveform, we could apply some fancy mathematics called a Fourier transform, and that'll take the complex waveform and break it back down to its component sine waves at different frequencies and amplitudes. And this analysis underlies a spectrogram display. And so to get a sense of that, we can take one of our complex waveforms that we created from the sine waves. So this is the 440 and 660 complex waveform. And the spectrogram shows frequency on the vertical axis, right? So this is higher frequency and this is lower frequency. And time in this direction. So this is the spectrogram down here, time for the waveform as well. And amplitude now is indicated by darkness of shading. And so this looks a lot different from spectrograms that you would see of speech because it's from sine waves. But you can see that the spectrogram found a bar at 440 hertz and another one at 660 hertz. And it also found the fundamental frequency, which is shown over here at 220 hertz. So it succeeded in finding both the fundamental frequency, the pitch, and the harmonics of given from this complex waveform. So we just discussed how the vocal folds vibrate at a fundamental frequency and then at higher harmonics. The vocal tract, that is the oral cavity and the laryngeal cavity and the nasal cavity as well, acts as a resonator. It amplifies some of the higher harmonics and dampens other ones. And then because the shape of the resonator, the vocal tract, is different across vowels because the tongue's in different positions and the mouth is shaped differently, you get a distinctive timbre. You get a distinctive amplification and damping of the harmonics. The parts of the spectrum that are amplified in vowels are called the formants. And the most important formants for vocalic distinctions are the first and second formants. In this chart, I've given you the average F1 values from a paper by Hillenbrand and colleagues. The fundamental frequency, which we call F0, was about 130 and 220 for men and women respectively. So these are the F1 values. These are the F2 values. And I've given you these as a sort of guideline for your work because I'm going to ask you to record everyone saying ba, bee, boo, boy, and bye with the same intonation for each word. So don't use a list. And then I'd like you to look at your vowels in Prot and using these average vowels as a guide to help find them, take the rough midpoint of ba, bee, and boo and try to find the F1 and F2. I'll show you, I have a link to a recording that I made. And this is
Ba.
ba. To help me find the formants, I used the under formants. There's show formants. Turn it off as it is on the default. Turn it on, and this is showing the first formant, and this is showing the second formant. And what you can see about the midpoint of the vowel is that the first formant is about 686. And if we went back to here, we can see that that's in the ballpark of the average F1 value. So I know that I'm looking at the right formant because that's the confusing thing about doing formant analysis is making sure that you're picking the right one, that when you think you're getting the first formant, you're getting that one. When you think you're getting the second one, you're getting that one. And remember, these are just average values here for the F1 and the F2. Your values may lie in between the male and female values, or may be lower than the male values or higher than the female values. They're just averages.